The Pantheon dome in Rome has stood for almost 2,000 years without steel reinforcement, while modern concrete structures built within the last century are already failing. And this contradiction begins with a volcanic ash mixture that allowed an ancient civilization to control gravity, water, and scale itself. Because Roman concrete was not simply a building material, but the operating system that made empire possible. And when it vanished, humanity would not fully understand what had been lost for over 1,000 years. Modern concrete is designed to fail. It cracks under stress and corrodes when water penetrates the surface and degrades within decades, which is why infrastructure built in the last century is already being replaced across the developed world. While Roman harbors poured 2,000 years ago still hold back the Mediterranean, and domes constructed before the fall of the Western Empire still shelter visitors in cities where modern sidewalks crumble within a generation. But Rome did not begin with this advantage, because for centuries the city remained trapped by the same material constraints that limited every ancient civilization, which meant walls rose slowly from quarried stone that was expensive to transport and impossible to shape into curves, while roofs depended on timber beams that rotted in moisture and burned without warning, which kept Roman cities locked in a cycle of collapse and rebuilding that consumed resources faster than conquest could replace them. The Greeks had mastered proportion within these limits, and the Egyptians had mastered mass, but neither civilization had broken the fundamental constraint, which was that architecture obeyed gravity absolutely, which meant the shape of every building depended on what its materials could bear before buckling, which meant roof spans rarely exceeded a few meters, which meant interiors remained cramped and dark, and public spaces required forests of columns to hold anything aloft. Rome inherited these limits. The Capitoline Hill held temples of timber and clay that impressed visitors but rotted from within. And yet by the 3rd century BCE, Roman ambitions were expanding faster than stone and wood could support, because military conquest was delivering populations and territories that demanded infrastructure at a speed no quarry could match, which created a problem that had no ancient precedent, because Rome needed to build faster and stronger and larger than any material in existence allowed. Rome needed something that did not yet exist. The answer came from volcanic soil along the Bay of Naples, where builders had noticed that ash from ancient eruptions behaved differently from ordinary materials, because when this ash was mixed with calcium oxide and water, it did not simply dry like mud. It transformed into something that bonded and reacted and hardened even when submerged in seawater, which meant for the first time in history a building material could cure underwater, which meant harbors could be poured directly into the sea, which meant Rome had discovered something no other civilization possessed. The mixture was deceptively simple: calcium oxide produced by heating limestone in kilns, water, and volcanic ash from the region around Pozzuoli, which would eventually give the material its scientific name. But the simplicity concealed a chemical reaction that modern scientists would not fully understand for 2,000 years. Because when volcanic ash containing reactive silica and alumina combined with calcium hydroxide and water, it triggered a slow molecular bonding process that produced calcium aluminate silicate hydrate crystals, which interlocked and hardened over time, which allowed the material to continue strengthening for decades and even centuries after it was poured. The chemistry was invisible. The results were not. The Romans did not understand the molecular process. They understood that their mixture outlasted stone. And the results changed everything, because this volcanic ash mixture could be poured into wooden molds and shaped into any form, which freed walls from precisely carved blocks, which allowed arches to curve continuously without keystones, which enabled vaults to span distances that stone lintels never could, which meant for the first time in architectural history form was no longer dictated by the limitations of material. Along the Bay of Naples, Roman engineers began testing this discovery in harbor construction, pouring concrete directly into the Mediterranean to create piers and breakwaters that still survive today, which proved the material could resist salt and pressure and time in ways that would have seemed impossible to Greek or Egyptian builders. And this was only the beginning, because the real breakthrough was not the mixture itself, but what it allowed Rome to build once gravity was no longer the governing constraint. But this created a question that would puzzle engineers for 2,000 years, because Roman concrete did not simply survive, it improved. Modern concrete cracks when water seeps through and corrodes when salt penetrates the rebar and fails within decades, which is why bridges and highways built after the Second World War are already being demolished across the developed world, while Roman harbor walls poured before the birth of Christ still hold back the Mediterranean without reinforcement or repair. The contradiction haunted materials scientists for generations, because every principle of modern engineering suggested that ancient concrete should have crumbled centuries ago, and yet samples pulled from Roman harbors showed the opposite, which meant something was happening inside the material that modern formulas could not explain. In 2017, researchers at MIT and the University of Utah published findings that changed how engineers understood ancient construction. Because when they examined Roman marine concrete at the molecular level, they discovered something that should not have been possible, which was that the concrete was still changing, still forming new mineral structures, still growing stronger 2,000 years after it was poured. The crystals were still growing. What they found was a rare mineral called aluminous tobermarite, which forms only under specific conditions of calcium and silica and alkalinity, and which had been growing slowly inside the Roman concrete for centuries as seawater seeped through microscopic cracks and reacted with the volcanic ash, which meant the very process that destroys modern concrete was strengthening the Roman version, which meant the Romans had accidentally engineered a self-healing material before the concept of chemistry existed. This was not a metaphor. The concrete was literally repairing itself. And the implications extended far beyond archaeology, because if Roman concrete could heal and strengthen over millennia, while modern concrete failed within decades, then the most technologically advanced civilization in history had somehow forgotten how to build permanent things, which meant the entire foundation of modern infrastructure rested on a material that was chemically inferior to what ancient builders had poured by hand, using volcanic ash and lime and seawater. Modern engineers are now attempting to reverse engineer what Roman builders knew by instinct, testing volcanic aggregates and calcium-rich additives in laboratories across 3 continents, trying to recreate a formula that was lost when the empire fell and forgotten for over 1,000 years. And yet the Pantheon still stands, the harbors still hold. The mystery is not what the Romans built, but why we stopped building it. But the real test of Roman concrete was not underwater, it was overhead. Inside the Pantheon in Rome, visitors still stand beneath the largest unreinforced concrete dome ever constructed, a span of 43 meters that has remained intact for nearly 1,900 years, without steel cables or internal supports, which should not be possible according to the structural physics that governed every building constructed before the Romans and most buildings constructed since, because the weight of a dome increases exponentially as its diameter grows, which forced ancient builders using stone or brick to construct domes only a few meters wide before the material collapsed under its own mass. The Pantheon represented not an incremental improvement but a fundamental break from everything that came before. The dome should not exist, and yet it does. The secret was not divine intervention but material control, because Roman engineers understood that concrete could be adjusted as it was poured, which allowed them to vary the density of the mixture from bottom to top, using heavier aggregates like basalt and travertine in the lower walls, where compressive strength was critical, and switching to progressively lighter materials as the dome curved upward, incorporating volcanic pumice and even hollow clay vessels near the apex, which reduced the load on the supporting walls by nearly half and enabled the structure to stand where solid stone construction would have buckled under its own weight. They also reduced weight through geometry, carving 28 coffered panels into the interior surface that removed mass without weakening the shell, and created a visual rhythm that draws the eye upward toward the opening at the center, and leaving an open oculus at the apex that spans nearly 9 meters and eliminates the need to close the dome at its structurally weakest point, while admitting a column of light that moves across the interior as the sun crosses the sky, transforming the building into a kind of astronomical instrument that tracks the hours and seasons through the play of shadow on concrete. None of this was accidental. The dome spans 43 meters. The height from floor to oculus is 43 meters. The interior geometry describes a perfect sphere that would touch the floor if completed, which meant every proportion was calculated to distribute stress evenly across the entire structure, which meant Roman engineers had developed a mathematical understanding of load distribution that would not be formalized in European engineering theory for another 1,500 years. The walls supporting this dome are 6 meters thick at the base, honeycombed with internal chambers and passages that reduce weight while maintaining structural integrity, and faced with brick and marble that concealed the concrete core from visitors who would never have known that the magnificent interior they admired was held aloft by poured rubble and volcanic ash rather than carved stone. And the Pantheon was not unique, because once Roman builders understood what concrete allowed, they began constructing interior volumes that no previous civilization could have imagined, spaces so vast and so structurally audacious that they redefined what architecture meant. The Baths of Caracalla, completed in 216 CE, enclosed a central hall with groin vaults that rose over 30 meters and spanned 35 meters without interior columns, creating a bathing space large enough to accommodate 1,600 Romans simultaneously beneath a ceiling that seemed to float on light admitted through massive thermal windows. All of it supported by concrete walls and vaults that still stand partially intact after nearly 2,000 years of earthquakes and looting and neglect. The Basilica of Maxentius, completed in the early 4th century, covered its central nave with 3 massive groin vaults that rose 40 meters and created one of the largest enclosed interior spaces in the ancient world. A structure so impressive that Renaissance architects, including Michelangelo, studied its ruins while designing St. Peter's Basilica, attempting to understand how Roman engineers had achieved spans and heights that seemed beyond the capabilities of their materials. These were not decorative achievements. They were engineering systems that solved logistical problems at imperial scale. And the scale was the point, because by the 2nd century CE, Rome had become the first city in human history to hold more than 1 million permanent residents, which created infrastructure demands that no previous urban system had faced, including housing density that required vertical construction on a scale never before attempted, water supply that required aqueducts spanning hundreds of kilometers across mountainous terrain, sewage systems that required tunnels beneath entire districts, public bathing facilities that required enclosed heated spaces large enough to serve tens of thousands of citizens daily, and food storage that required warehouses capable of holding grain for a population larger than most modern cities. Concrete made all of this possible. Beneath the streets of ancient Rome, concrete lined the channels of the Cloaca Maxima, the great sewer that had been draining the Forum Valley since the 6th century BCE, but which was expanded and reinforced over the following centuries, with poured walls and vaulted ceilings that still function today, carrying rainwater and waste through tunnels that have outlasted every government that ever ruled the city above them, which meant Roman sewage engineering has now been operational for about 2,600 years and shows no signs of structural failure. Above the streets, concrete formed the cores of insulae, The apartment blocks that housed the working and middle-class population of Rome in structures that rose 5 and 6, and sometimes 7 stories above the street, and packed families into dense vertical neighborhoods that maximized land use in a city where real estate near the center was already impossibly expensive, which meant Rome had solved the problem of urban density nearly 2,000 years before London or Paris or New York faced the same constraint. Using a material that allowed rapid construction and standardized design and load-bearing walls thin enough to maximize interior space. The insulae were not elegant. They were prone to fire and collapse and were frequently criticized by Roman writers for their crowded and uncomfortable conditions. But they housed 1 million people in a city that could not expand horizontally, and they did so using construction techniques that would not be matched in Europe until the industrial age made steel frame buildings possible. Across the empire, concrete standardized construction in ways that allowed Roman engineering to spread with Roman conquest. Because the same mixture that worked in Italy could be adapted using local volcanic materials in Gaul and Germania and Hispania and North Africa and the eastern provinces, which meant aqueducts and baths and amphitheaters and harbors could be built to consistent specifications across 3 continents using local labor trained in standardized techniques, which meant infrastructure became a tool of imperial integration as powerful as law or language or military occupation. The numbers are difficult to comprehend from a modern perspective. The aqueducts supplying Rome alone delivered about 1 million cubic meters of fresh water to the city every day, enough to provide each of the city's million residents with roughly 1,000 liters daily, a volume of municipal water supply that would not be matched by any European city until London expanded its water infrastructure in the 19th century. These were not estimates. These were operational realities. The baths of Diocletian could accommodate over 3,000 bathers simultaneously. The Circus Maximus seated about 250,000 spectators. The Colosseum held 50,000. The warehouses along the Tiber stored grain sufficient to feed the entire city for months. No other ancient civilization operated at this scale. No other civilization had the material to make it possible. Somewhere in the 2nd century, a Roman laborer stood waist-deep in Mediterranean water, watching concrete harden around the wooden forms of a harbor extension, unaware that the mixture settling against his legs would still be holding back the sea 2,000 years after his bones had turned to dust, unaware that engineers in a future he could not imagine would cut samples from this same wall and study them under instruments he could not comprehend, trying to understand what he and his fellow workers had poured without fully understanding themselves. He finished his shift, the concrete cured, the harbor held, it is still holding. And none of it would have been possible without a material that no one celebrated, because concrete was never beautiful and was never meant to be seen. Hidden behind marble facades and brick veneers and painted stucco that made Roman buildings look traditional, even as their cores were revolutionary, which meant the material that held the empire together was invisible to everyone except the builders who poured it, which meant when the knowledge of how to make it was lost, almost no one noticed until the buildings stopped being built and the ones that existed started falling down. And this invisibility reveals something deeper about how Romans thought, because to build in concrete was to accept that the surface and the structure were different things, that appearance served politics while engineering served permanence, that what visitors saw when they entered a basilica or a bath or a temple was not what held the weight or would determine how long the building stood. This was a civilization that trusted what worked more than what impressed, that valued infrastructure over ornament, that built roads not because roads were beautiful, but because legions needed to move and merchants needed to trade and information needed to flow, that built aqueducts not because aqueducts were elegant, but because cities needed water and fountains, needed pressure and baths needed supply, that poured concrete into foundations and harbors and sewers and walls not because anyone would admire it, but because someone would rely on it for centuries after the builders were dead, and the emperors were forgotten, and the language itself had evolved into something the original speakers would not have recognized. The Romans did not build for tomorrow, they built for time, and this mindset extended beyond engineering into how they organized knowledge itself. Because the architect and engineer Vitruvius compiled detailed instructions for mixing and applying concrete under different conditions in his 10-volume treatise on architecture written in the 1st century BCE, specifying ratios of volcanic ash to lime for foundations and for harbor works, and for structures exposed to moisture, and for walls that would remain dry, which meant the formula was not a craft secret passed from master to apprentice, but a documented and teachable technology embedded in texts that could be copied and distributed and preserved across generations, which meant Roman concrete was institutional knowledge, maintained by institutions, and vulnerable to institutional collapse. But institutions require stability, and stability was precisely what the Western Roman Empire could not maintain after the 3rd century CE. Because a cascade of political crises and military defeats and economic contractions and administrative failures gradually dismantled the networks that had made large-scale Roman construction possible, so that the quarries that supplied limestone and the kilns that produced calcium oxide and the ships that transported volcanic ash from the Bay of Naples to construction sites across 3 continents gradually fell into disuse, or were captured by hostile forces, or simply stopped operating, because there was no longer demand for their products or payment for their workers. The formula itself was not secret, it was written down, but formulas require materials, and materials require supply chains, and supply chains require functioning economies and stable governments and predictable trade routes, none of which existed in the Western Mediterranean after the 5th century. When the Visigoths sacked Rome in 410 CE, they did not burn the libraries or destroy the engineering manuals, but they disrupted the economic systems that made those manuals useful. And this meant builders who knew how to read Vitruvius could no longer access the specific volcanic ash that made his formulas work, which forced them to substitute local materials that lacked the reactive silica and alumina content of true pozzolan, which created concrete that did not trigger the same chemical reactions and did not develop the same crystalline structures and did not heal itself over time and did not last. Within a few generations, the difference between Roman concrete and post-Roman imitation concrete became visible in every structure that used it. At the same time, the demand for large-scale construction collapsed along with the population of Roman cities, because urban centers that had held hundreds of thousands of residents shrank to tens of thousands or fewer, which eliminated the need for massive bath complexes or apartment blocks or grain warehouses, which destroyed the market for the engineering knowledge that had built them, which forced skilled workers to disperse into the countryside or die without training replacements, which ensured the techniques for adjusting concrete density and calculating load distribution and constructing formwork for massive vaults were not rejected or suppressed, but simply forgotten because no one needed them anymore. The formula vanished for 1,000 years. Medieval builders looked at Roman ruins and marveled at their scale, but could not understand how they had been constructed, because the idea that walls and domes and vaults had been poured, rather than assembled from carved blocks, seemed impossible to people who had never seen concrete made or used. So they assumed the strength of Roman structures came from the size of the stones or the skill of the masons, rather than the chemistry of the binding matrix. And this meant they tried to replicate Roman forms using masonry techniques that could never achieve Roman performance, which forced European architecture to regress to smaller spans and thicker walls and darker interiors and lower domes for nearly a millennium after Rome fell. the Hagia Sophia in Constantinople, completed in 537 CE under the Emperor Justinian, used some concrete techniques in its foundations and pendentives. But even this late imperial masterpiece shows the knowledge degrading, because the original dome collapsed after an earthquake in 558 CE and had to be rebuilt with modifications. And the rebuilt dome cracked repeatedly over the following centuries and required additional buttressing, which suggests that the precise understanding of Roman concrete engineering had already faded beyond reliable reproduction, even in the Eastern Empire, where continuity with Roman institutions was strongest. In Western Europe, the loss was total. For nearly 1,000 years, no one built anything that matched what Rome had poured before the empire fell. The rediscovery came not from archaeologists or historians, but from engineers facing practical problems. Because in the 18th and 19th centuries, industrial Europe needed building materials that could support factories and railways and bridges and tunnels at scales and speeds that traditional masonry could not provide. And so chemists and builders began experimenting with calcium-based binders and hydraulic cements that could set underwater, which led eventually in 1824 to a British bricklayer named Joseph Aspdin patenting a new artificial cement he called Portland cement, because its color resembled the pale limestone quarried from the Isle of Portland in Dorset. Portland cement was not Roman cement. It was made from limestone and clay rather than limestone and volcanic ash, and it set through different chemical reactions, and it reached full strength within weeks rather than continuing to strengthen over centuries, and it did not form the tobermorite crystals that gave Roman concrete its self-healing properties. But Portland cement was cheap to produce and fast to set and strong enough for the needs of the industrial age, which meant it became the foundation of modern concrete. And modern concrete built the 20th century, from highways stretching across continents to skyscrapers rising in every major city to dams holding back rivers to foundations supporting everything the modern world required. The scale of modern concrete production is almost incomprehensible. Humanity now produces about 4 billion metric tons of cement annually, making concrete the second most consumed substance on Earth after water. The infrastructure of the modern world, every bridge and highway and building and tunnel and dam, rests on this single material, and this material is failing. Not dramatically, not catastrophically, but steadily and expensively and inevitably. Because Portland cement concrete reaches its maximum strength within weeks of pouring, and then begins a slow process of degradation, as water penetrates the surface and reacts with the calcium compounds inside and corrodes the steel reinforcement that modern engineers embed in their concrete to compensate for its tensile weakness. Every structure built with modern concrete carries an expiration date, typically between 50 and 100 years, depending on conditions and maintenance. The bridges built to carry the interstate highway system across the United States in the 1950s and 1960s are now reaching the end of their design service life simultaneously. And the American Society of Civil Engineers estimates that over 40,000 bridges in the country are structurally deficient, and that the cost of repairing or replacing the nation's deteriorating infrastructure exceeds $4 trillion. That number is so large it represents not an engineering problem, but a civilizational one. And the problem is not limited to the United States, because every developed nation built concrete infrastructure during the same post-war period using the same Portland cement technology with the same built-in expiration dates. This created a situation where the entire developed world faces the same replacement crisis at the same time, compounded by the fact that cement production generates about 8% of global carbon dioxide emissions annually, which ensures that rebuilding 20th century infrastructure using 20th century methods would accelerate the climate crisis that is already straining those same systems. The Romans did not face this problem, because the Romans built for eternity and we build for quarterly earnings reports. This is not a metaphor or an exaggeration, but a measurable difference in engineering philosophy with measurable consequences. Because Roman harbor concrete has now been submerged in corrosive seawater for over 2,000 years and continues to strengthen, while modern marine concrete requires maintenance or replacement within decades, which means Roman engineers using hand tools and volcanic ash achieved results that modern engineers using computers and industrial chemistry cannot match, which means something was lost when the formula was lost, something beyond chemistry. In laboratories at MIT and Berkeley, and the University of Utah and research institutions across Europe, scientists are now analyzing samples of Roman concrete at the molecular level, mapping the crystal structures and chemical compositions and reaction pathways that produce the self-healing properties ancient builders achieved by instinct. And some of these researchers are attempting to recreate Roman-style concrete using volcanic aggregates and seawater and slow-curing binders, testing whether modern materials science can recover what ancient observation discovered. The results are promising. Experimental concretes using volcanic ash and calcium-rich seawater have produced tobermorite crystals under laboratory conditions. Some researchers have demonstrated self-healing behavior in specially formulated mixtures. Others are developing cements with lower carbon footprints that might also prove more durable. But recovering the formula is not the same as recovering the mindset, because Roman concrete was not just a material, but an expression of how a civilization thought about time and responsibility, and the relationship between present convenience and future consequence. And modern civilization has largely abandoned that way of thinking in favor of planned obsolescence and deferred maintenance, and the assumption that problems can be pushed forward indefinitely for future generations to solve. The Pantheon dome weighs over 4,000 metric tons. It has been standing for nearly 1,900 years. It will probably still be standing when the last highway overpass built in the 20th century has been demolished and rebuilt 3 times. Inside the ruins of Roman harbors along the Mediterranean coastline, concrete walls still hold back the sea, their surfaces rough and weathered but their cores intact, still forming crystals, still healing, still growing stronger than the day they were poured, while modern piers built nearby crumble and require replacement. In the foundations beneath the Colosseum, concrete poured before the empire reached its peak still supports the weight of tourists who climb through the structure 2,000 years later, unaware that they are walking on a material more durable than anything their own civilization knows how to make. And in those ruins and foundations and harbor walls is a question that the 21st century has not yet answered. We know how they built it. We are learning why it lasted. What we have not decided is whether we are willing to build that way again, whether we can accept slower curing times and higher initial costs and materials that serve generations rather than fiscal years, whether we can think about infrastructure the way the Romans thought about infrastructure, as something that should outlast the people who built it, and the governments that commissioned it, and the economic systems that financed it. The Romans poured concrete into the Mediterranean 2,000 years ago, and it is still there, still holding, still healing. The crystals are still growing. The question is not whether we can build like Rome. The question is whether we will.